Right. So last time we were talking about the dipole moment, sorry, the magnetic field at the center of a loop. So we had a loop of wire that's something like loop of wire goes this way. Here's the back. Here's the front. And we used the Biot-Savart law by integrating the current to establish what the magnetic field is along the center line. Right. And we found that at a particular point, say z units out from the center, and let's say that this has radius r, we found that the magnetic field at 0, 0, z, and there's a standard set of axes that we need, say x, y, and z. Oh, that's a z and z, right? In those coordinates, we found what the magnetic field is along the central axis, and it is mu naught I r squared divided by 2 times r squared plus z squared to the 3 halves in the k hat direction, meaning it points in the z direction. So so what we can establish from this formula is that for a loop of wire, sorry, a loop of current. So often, by the way, I will say a loop of current. What that means is that there's current flowing through a loop of wire. A loop of current produces a dipole field along its central axis. And by the way, the reason why we know it's a dipole is because it has the properties of the dipole that we described last time. It experiences a torque and so on and so forth. But it also has another property that dipoles should have, which I'm about to get to. So it produces a dipole field along its central axis that falls off as 1 over r cubed, where r is the distance, little r is the distance between the dipole and the point of interest. And this is just like the electric case. So that was that's just another way in which this loop of current produces a dipole. It has the same asymptotic behavior. It goes as 1 over r cubed, and you can check that by just letting z go to infinity or become large compared to r. Then that denominator becomes 1 over z squared to the 3 halves, and that's just z cubed, right? And z here is the measure of how far away the point is from the center of the dipole, or of the loop of current. Further, another point that's useful to reference is that the field along the axis of rotation, like along this axis, points in the same direction as the area vector, right? So remember, the area vector for mu is the vector that points in the direction or points perpendicular to the loop. And just as just like how you had a displacement vector for an electric dipole, this was the vector that points from one of the charges to the other charge, from the negative charge to the positive charge. The produced electric field along that direction was in the same direction. The same applies here. So the produced magnetic field points in the k direction, as does the area vector A. So they match up. So this is all just to say that all of the properties that you might expect from an electric dipole, the magnetic dipole has very nearly the same properties. Hence, we can refer to a loop of current as a dipole. It is a magnetic dipole. So if we were to actually try to draw the magnetic field around a loop of current, kind of more generally, it would look something like this. So you have a magnetic field through the center, and then it would go like that, and like that, and like that, and like that, and so on. And so if you were to zoom out really, really far so that the loop looks small, this would look a lot like the field near an electric dipole, right? An electric dipole produces a field like this just as well, where these, loop around and close up. So the relationship is there. And by the way, just so this picture is clear, say mu points this way. in this case. Right. So the next question, and it's kind of the obvious next question to ask, is what happens if you have a whole bunch of these loops stacked on top of each other? So that is what's called a solenoid. So a solenoid is what happens if you stack n loops so they formed a coil. Of, say, length L. I can spell. You form a solenoid. So a solenoid is really one continuous piece of wire that's coiled on itself. And that's basically equivalent to just taking a whole bunch of loops and then just stacking them on top of each other. Like they're effectively the same. So the picture here, and this is going to be a terrible drawing, but it looks something like this. It's just a big coil of wire with length L, and it has, say, n turns. That's the language that'll often be used. A solenoid has so many turns. It turns around so many times. And so we can actually define, oh, almost dropped my pen. We can actually define the notion of turn density, which will become useful later. And we ascribe to that notion lowercase n, and that's just the number of turns per unit length of the solenoid. So it would be like the turn density is the number of turns in, say, 1 meter of length. Most solenoids are not that long, but you could have a turn density of 500 turns per meter, and so you would have 5 turns over the course of a centimeter. That's all it is. And typically we assume turn density is constant. So typically when we're handling solenoids, and this is the case for most of this course, we want to know the field inside the solenoid. So we typically assume that the solenoid is very long. Whenever we're solving a problem. Now, I mean, there are going to be problems where it's a finite solenoid, but at least for the simple case, we're just going to assume that it's very long, infinitely long, and that will let us easily solve for the magnetic field in the center. For the magnetic field along the center line. So the picture is we want to know what the magnetic field is along this dotted green line. We want to know what direction it's in, what value it has, and so on. And so if the solenoid is sufficiently long, we can find it anywhere. In fact, if it's infinitely long, then you can find it everywhere along that center line, and it can be relatively easy. So we're just going to compute this directly using the Biot-Savart law, sort of. So to compute this, we're going to use the magnetic field from a single loop, which we had already computed, right? We computed that last time, and it's at the top of this page. And the reason we can do that is because all we're going to do is we're going to figure out how much current is going through a single loop of this solenoid, and then add up all of the contributions from the magnetic field using the superposition principle. Now, we are going to kind of generalize a little bit. We're going to assume our loops are infinitesimally thin, so that you have a continuous amount of loops, and then you have a turn density rather than like discrete actual wires, just because it makes the calculation a lot more straightforward if you do that. So so the picture that you'll often see is you'll see a cylinder. Oops. And this cylinder has current flowing around the side. And so a loop, which might be infinitesimally thin, would be just an infinitesimally thin ring around which current flows. And so let's just say that, and we'll do that. We have to do an integral, right? So by the way, this is infinitely long, so it extends in both directions. So what we're going to do is we're going to add up contributions from each slice. And each slice corresponds to a loop, using the B field for a loop. So the first question that we need to answer if we want to use that formula is how much current does a slice of thickness dz have? And the reason we need that, by the way, is because if we look up at our formula, it involves the amount of current in that loop. So if we're going to treat a slice as a loop of current, we have to know how much current is in it. Given a slice of thickness dz, how much current does it have? And by the way, this is the standard thing that we're doing. It's just like we've done this for lines of charge, where we look at an infinitesimally small length of charge and we ask how much charge a length of, or a segment of length dz has. So it's the same thing. It's just here it's current flowing through or flowing around that slice. So to answer this question, we need to know how much current is actually flowing through the solenoid, i.e. you have a wire coming off here and a wire coming off here. How much current goes in and how much current goes out? We need to know those. Right, so that's just something that you might be given. At least in this case, I'm going to assume it's given. So the whole solenoid has current I. And a segment of length L. So a segment meaning like a chunk of solenoid of some length has current. And so this would just be like treating that whole segment as a really thick wire. So you have a really thick loop. So you have a whole bunch of loops through here. So how many loops do you have? And then combine that with the current in each loop. And then we're going to use this relationship to figure out how much current is in a really thin loop. Right, so a segment of length L has, let me put the word effective, has effective current given by the number of turns in that length times the current, right? So if there were 5 turns and each one had 5 units of current, if there are 5 turns and each one has current I, then the total current that goes around a segment of length L would be 5 times I, right? And so we can actually rewrite this in terms of turn density just by writing that capital N is equal to little n times L. So this is equal to NL times I. So that means we can figure out the current in a slice of length L. You just multiply n times little n times I by the thickness of our slice. And so if we have a slice of thickness dz, we can figure out how much current is in that slice. So a slice of thickness dz, dz for those non-Americans, it would have current Ni dz, right? That is the amount of current that would be flowing through the that little infinitesimally small slice. And so the idea here is, imagine that, this might be like a fraction of a wire, like a real wire might have some thickness. You are asking how much current is flowing through just a little fraction of that wire, where the thickness of that fraction is dz. So from there, we can figure out what the let me erase that. We can figure out what the magnetic field contribution is from that slice. So before we do that, let's actually, I'm just going to draw a picture here, or I'm going to amend this picture slightly. I'm going to put, actually, no, that's fine. Oh boy. What just happened? Went to the other sorry. What? Okay. I'm going to have to redraw this back into the picture. So we have our little infinitesimally small slice, current going around it, equal to n times I times dz. Let's say we want to know the magnetic field at that point. So it's along the center line, but we don't know what the value is. All we know, actually, let me put it, say here. Sorry, no, here's good. So in this picture, we will call, just trying to make sure that this is easily digestible. Yeah, that's fine. Okay, so we're going to call this distance z, and we're just going to say that this occurs. Oops. Sorry. We're going to say that this height above the, say, the z-axis, say this is z equals 0 here, that height is z, and this will be, I'm just trying to make this so easy. Actually, just for the sake of argument, let's make this z equals 0, and let's make the point that we're interested in finding the magnetic field, let's call that z. So the reason why I'm doing this is so that we can line up this picture with the, no, that's not what we want to do. Let's call this z equals 0, and this will be at some position z. Now, in this case, z will be negative, but that's fine. All right, this is what I'm sticking with. So the reason why I'm doing this is because we want to be able to integrate over the variable z. So we would like to go from negative z is infinity to positive z is infinity and figure out the contribution from each of these loops at that point z equals 0. Now, the only thing that will be a little bit challenging is we have to figure out what is, so the z here represents the distance between the center of our loop and the point of interest. The z here is not necessarily the same thing. This is, I mean, it's still true that this distance would be the absolute value of z, but truly, sorry, but truly, yeah, so let me just leave it at that. So if we wanted this distance, that would in fact be the absolute value of z. And that's only the case because in this case, z is negative because it's below the z equals 0 line. That's all. Sorry for that, a bit of a ramble, but I wanted to make sure that this picture is clear. Right, so from that perspective, or rather from that loop of wire, that loop of current at position z, the distance from z to the point of interest, POI, is the absolute value of z. And so we can use that formula, we can replace the letter z here with the absolute value of z and then just use this formula directly. So that implies that the magnetic field, the magnitude of the magnetic field rather, from that small loop of current at position z would be equal to mu naught times r squared, where r is the radius here, times the current. In this case, the current is n times I times dz. So I'm just tracking here. So I'm just looking at this term. So mu naught times n times I times dz times the radius squared divided by 2 times this particular function. And I will write it out here. 2 times r squared plus, now here I should plug in the absolute value of z, but I'm about to square it anyway, so I can get rid of that absolute value. So 2 times r squared plus z squared to the 3/2. So that's the contribution from to the that is the magnitude of the contribution at that point of interest labeled here. I'll mark it in blue. From the loop at position z. Now, we can't just integrate the magnitude, at least we can't without knowing something else, because in principle, the magnitudes could be the same or something, but they could be pointing in different directions. But what we have to do here is we have to note that every slice produces a component, or produces a contribution to the magnetic field that's proportional to the k-hat direction, or that's parallel to the k-hat direction. And the reason we know that is because along the center line of a loop, the magnetic field always points in the k-hat direction, as we established there. It doesn't matter how far away from the loop you are, as long as you're along the center line, you point in the direction perpendicular to the loop. And so because the current is running through each one of them in the same direction, they always point, in this case, up. So the magnetic field will always point up from every single chunk. So we can just integrate the magnitudes, and then that will tell us the final magnitude, because they all point in the same direction. So what this says is we can just integrate the magnitudes. So that means that the B field, magnetic field, along the center line can be just computed relatively easily. Of a long solenoid, I should specify that. If your solenoid is small or short, then it will have non-trivial effects, because we can't treat it as infinitely long anymore. Right. So the B field along the center line of a long solenoid is, well, it's the magnetic field is, the magnitude is mu naught times r squared times ni divided by 2. So I just pulled out the constant things from here, and then we're going to do an integral times an integral from negative infinity to infinity, assuming it's infinitely long. So there's an infinite number of these slices above and below. And then we integrate dz. We're adding up all of these segments of, or loops of current, plus z squared to the 3 hats. And we've done this sort of integral before. It works out to be 2 divided by r squared. So that means that the magnitude of a long solenoid, the magnitude of the magnetic field along the center line of a long solenoid, is just mu naught times m times I, which is a really, really wonderfully nice and simple formula. By the way, the thing to take away from this picture is that this is kind of like an infinitely long solenoid is kind of the magnetic equivalent of an infinitely large plane of charge. It has a constant magnetic field. And we'll actually see what happens away from the center line and outside of the solenoid after either later today or on Tuesday. So away from the center line, like let's say you were looking at a point that's over here, right? Away from the center line, it's not really different. And that's because the magnetic field within a solenoid is basically uniform. Like it's approximately constant throughout the entire solenoid. And that's even true for non-infinitely long solenoids. It's approximately uniform. The reason why is basically, and we will explain this in more detail later, but it's basically because the magnetic field doesn't depend on the size of the solenoid, right? So it shouldn't matter where, like the magnetic field in the center doesn't depend on the radius of the solenoid. So it would make sense that if the solenoid is really, really giant, then you could move away from the center line without changing very much, because you're not really getting that much closer to one side than the other. And so because you can keep the magnetic field along the center line the same, even though you change the radius, you can just make the radius of the solenoid huge so that the magnetic field in the middle is uniform. And then you can shrink it back down and you observe the same effect. That's a heuristic argument, and we will make it more formal later today if we get there. It also follows that outside of the solenoid, like say on the side, like say over here maybe, the magnetic field is very nearly 0. And for infinitely long solenoids, it's in fact exactly 0. And again, we will be able to explain that later today. So the question then is, what does the magnetic field look like? So the magnetic field for a solenoid is actually a relatively, for like a finite real world solenoid, looks like this. So you have your solenoid, finite length, right? I tried to draw it well. So the magnetic field, we know the magnetic field along the center line points this way. And so if you were to go and do this calculation for a real world finite length solenoid, you would find that the magnetic field looks like this. That's not a great approximation, but and sorry, that's the wrong direction. And oh boy, in fact, those, I'll just redraw it. Those field lines will close back in on themselves. Yeah, so it behaves a lot like a long dipole. Or if you zoom out enough, it just behaves like normal dipole. So just like how a single loop of current is just a dipole, this is just a dipole. And so the magnetic field lines are very similar to those of a permanent magnet. And so what we can do with modern technology is we can use this idea of large solenoids with a lot of current running through them to effectively create like a permanent magnet that you can turn on and off by just cutting the current. And you could even tune the current or tune the magnetic field by changing the current that you're letting go through the solenoid. And so this is what we call an electromagnet. Depending on how much electricity you go through the coil of wire, you get more magnetic field. And in fact, like this is what they use in those like car moving vehicles that like pick up cars in junkyards and move them elsewhere. They just turn on a really powerful electromagnet, go close to a car, which picks it up, and we'll explain why that works later. And then they take it where they want to go, and then they turn off the electromagnet and it falls. And so you can effectively get away with controlling when you have magnetism really, really easily. And you can't do that very much with electric fields because there's either charge or there isn't. I mean, there are ways that you can create pseudo electric fields by using changing magnetic fields, but even that's challenging. So magnetism actually gives you, like, if you can create electromagnets, you get a lot of control over useful things. That's why magnets are so cool. Right, so now we're going to get to the $1 million question. How do permanent magnets work? So we've established how electromagnets work. They're just there's a bunch of loops of wire that have electricity running through them. But permanent magnets are a different story. They don't require any energy being put through them to establish their magnetic field. So for the sake of this course, we're going to assume that all atoms have some magnetic dipole moment. It's not actually true that they all do, but most atoms will have some amount of electric dipole moment. And the reason why is that the electrons, quote unquote, orbit their nuclei. And we know that if you have charges moving in a circle, you produce a dipole moment. So even though this isn't actually true because there's quantum mechanics and stuff involved, you can imagine that at least in a simple model, if the electrons just go in circles around their nucleus, then that will produce some sort of magnetic dipole moment. Also, just to make things more confusing, there's something called quantum spin that electrons have, and that also produces a magnetic dipole moment. Sorry, magnets are hard, and real world permanent magnets are confusing. But the gist is that if you take some random atom, it will probably have an electric or a magnetic dipole moment that points in some direction. So the question then is, how do permanent magnets form? Maybe a little bit. I don't remember off the top of my head. So the way you form a permanent magnet is you take a majority of those little dipoles and you line them up. So when you take a whole bunch of little dipoles and you line them up, the resulting effect is reinforces the magnetic field that each one produces. There is quantum, but I don't know if you'll talk about quantum spin. I don't remember off the top of my head. It's been a long time since I've TA'd for 9D. So the net result here is that you get a macroscopic, i.e. a visible on the human level, dipole magnetic field. So what that amounts to then is that the permanent magnets just behave like dipoles with their corresponding forces, with whatever corresponding forces that you have. And so this process where you have these small individual atomic dipole moments, when they're all lining up, a property, or the name of the property that objects that experience this have is called ferromagnetism. So objects that are ferromagnetic are objects that tend to have their dipole moments in all of their little atoms, materials that are ferromagnetic, like iron, nickel, cobalt, and so on. These are materials that tend to be energetically favorable to having all of their dipole moments line up. Now, there's this business about domains and how really it's not individual dipoles being randomly aligned. It's you have chunks of dipole moments that are randomly aligned with other chunks. And so those are called domains. And so in a ferromagnetic material, most of the domains line up and you have relatively large domains, but that's neither here nor there. You can read more about it in the Liber text. But the basic idea is that you have a whole bunch of dipoles that are all lined up inside your chunk of iron. And so the net result is one large dipole moment. And if you have a few that are, slightly misaligned, you're still going to get an overall dipole moment that's larger than the sum of than any one of the individual dipole moments. Can you also induce dipoles to create a temperature? Yes, we're going to get to that. So the first question is, so that's why some metals and some materials are magnetic. It's because they have this property called ferromagnetism, which basically allows for their dipole moments to line up and produce a macroscopic magnetic field. Sorry, a macroscopic dipole field, which is a magnetic field. So then the question is, why is it that ferromagnets stick to non-ferromagnetic things? Stick to some non-ferromagnetic things. Now, this should be surprising because as far as we've, so this is a natural property of certain elements, basically. So as far as we can tell, as far as we have covered in this course, the only time you get a force between a magnetic force between two things is if you have two dipoles, right? If you have two dipole moments, or you have two things that both create magnetic fields, you'll get a force between them. You get a force between them that's a result of the dipole of one being attracted to the change in magnetic field of the other, right? So at the very, actually, I think this was from last lecture. We had this idea where you have you have a permanent magnet that produces a magnetic field. Then we saw that a dipole, like a loop of current, would feel an attraction or a repulsion from that magnetic field because it also produced its own magnetic field. If you have something that just doesn't produce a magnetic field, you would think that it would experience no force. So what happens is that the dipoles in the non-ferromagnetic material, the reason why this can't happen, like you can stick a magnet to a refrigerator, even though your refrigerator is not magnetic, the dipoles in the non-ferromagnetic material are random i.e., and hence you don't get a magnetic field. But they're free to move, or they're free to rotate. So what you get is you get a magnetic field from, say, from a permanent magnet, right? And then you have a whole bunch of randomly aligned dipoles in your other material, right? But under the influence of this magnetic field, we know what happens to dipole moments that are free to rotate. They experience a torque. And so all of these dipole moments in this separate type of material experience a torque that line up their dipole moments with the external magnetic field. So in the presence of an external magnetic field, and that external magnetic field might be provided by a permanent magnet, they experience a torque. Let me be more specific. The microscopic dipoles experience a torque, forcing them to align with the magnetic field. Because that's what dipoles do in the presence of a magnetic field. They experience a torque that aligns them with that magnetic field. And then the moment they're all aligned, now you just have another magnet. You have a bunch of dipoles that are all aligned with each other. And so you would have a whole bunch of dipoles that are aligned this way. And so that will make this end the south end. And so now the north and south ends can attract, and you get a magnetic object that is made a non-magnetic object temporarily magnetic, and so they attract each other. So this property, materials that have this property where the dipoles are free to rotate, those are materials that are called, or those materials have the property of paramagnetism. So not all materials are ferromagnetic, not all materials are paramagnetic. There's also another type of magnetism called diamagnetic, and that means that in those materials, the dipoles actually anti-align for a more complicated reason. But so those materials tend to cancel out external magnetic fields. And so this is how you can like levitate like frogs with magnetic fields, because water is diamagnetic. So it would repel external magnetic fields. And so it will create a repulsive force between the magnetic field and the object. Will they keep that up? No. So that's the important point. When the applied magnetic field disappears, with a strong enough magnet, you can levitate anything. When the applied magnetic field disappears, the dipoles randomize again. So the difference between a paramagnet and a ferromagnet is that a ferromagnet is a type of material, and by the way, it's not just a material property, it's also like the condition of the object. So like iron, like typically iron is paramagnetic when you just like find iron in the ground, but you can magnetize it. You can magnetize it by basically heating it up and exposing it to a very, very high magnetic field, a very high external magnetic field. And then when you cool it back down, while that magnetic field is still present, you can kind of lock in that arrangement of dipoles, which takes this piece of iron from being paramagnetic to ferromagnetic. And so, sorry, no, iron is ferromagnetic, but the domains are typically small. You can break those domains up and reform them by bringing them to a high temperature. There's a good discussion of this in the Liber text that I'm not going to go over because it's material science, and while it's interesting, there's not a whole lot of physics involved. I mean, there is, but it's not something that is fundamental. But the idea is if you want to take something that's magnetic and make it not magnetic anymore, or at least not macroscopically magnetic, like a chunk of iron, heated up past its Curie temperature, which is the temperature at which magnetism disappears for a particular material, and then you just cool it down and it will be non-magnetic. Or if you want to make something non-magnetic that is otherwise ferromagnetic and make it actually have a macroscopic magnetic field, heat it up past its Curie temperature, which is some high temperature, expose it to a very large magnetic field so that you force all of its dipoles to align at that high temperature, and then slowly cool it down. And those magnetic fields will stay aligned. It's kind of neat. Right, so that's how permanent magnets work. Now you know, now you can answer the question, magnets, how do they work, right? Anyway. So we're going to kind of change gears. We're still talking about magnetism, but we're going to go back to talking about electromagnets, basically. So we're going to talk about Ampere's law for the remainder of the lecture today. Yeah, magnets are just tiny magnets. It's true. So we've already established that Gauss's law for magnetism is not very interesting. It's just that the magnetic flux through a surface is 0 because there's no magnetic charges. I mean, it's interesting in that it tells us that there's no such thing as magnetic charges, but it doesn't really help us calculationally. It doesn't help us figure out what the magnetic field is, like Gauss's law does for the electric field. Because for the electric field, you can figure out what the magnitude of the electric field is at any given place using Gauss's law. But there is a separate law for magnetism that works similarly for magnetism as Gauss's law does for electricity. So I'm just going to remind you, we're going to take a little bit of a detour. Kirchhoff's loop rule is the following statement. I promise this is related. Is the statement that the change in voltage around a loop is 0, right? That's Kirchhoff's loop rule. So as an integral, we could convert that to an integral of the electric field, right? Because the change in potential is just a line integral of the electric field. So we can write that Kirchhoff's loop rule as the integral over a closed loop, a closed line integral, that's what the circle means, of E dot dl equals 0. Now I have to give the caveat here that actually this is only true in the statics case when there's no magnetic field present. So take this with a grain of salt. It is more or less correct, but just take it with a grain of salt. And so Ampere's law, which is this magnetic equivalent of Gauss's law, is the same thing. So the point I'm getting at is that for electricity, we have Gauss's law says over a closed surface, we have E dot dA is equal to Q enclosed, let me use capital Q, Q over epsilon naught. And what we just established is that E dot dl for a closed loop is 0. Now, one thing that we've already established for magnetism, and by the way, this is getting to Maxwell's equations. For magnetism, we've already established that B dot dA is 0. So you might be able to guess that we should have some sort of magnetic, and there's sort of this duality between lines and surfaces, between electricity and magnetism, as you may have already kind of intuited. But you might expect that you get something like a loop integral B dot dl is equal to something. And you'd be correct. You'd 100% be correct that this is also, like, there is a relationship about magnetic fields that has this form. And in fact, the relationship that this describes, this is Ampere's law. And we're going to be more formal about it. I'll actually give you the formula for it later. But that's why you kind of expect there to be something like this, because you have that the line integrals, that the line integral for one is 0, the line integral for the other isn't. The surface integral for one is 0, the surface integral for the other isn't. There's this kind of this duality. So let's think, what could that integral actually be equal to? So for the electrical Gauss's law, it was the enclosed charge, right? So the equivalent here would be some sort of current. So if we're talking about electricity, we have charge. So what is the equivalent for magnetism? What is the charge equivalent of magnetism? Well, we know that the way you produce electrical fields or electric fields is with having some charge. The way you produce magnetic fields is having some current. So we should have that B dot dl is something involving current. At least if we want to have this duality be maintained, right? And we do, because, you know, electricity and magnetism seem to be very closely related. So the question is how do we figure out what that something is? So again, looking back to the electrical Gauss's law, a charge was enclosed, like this charge that we refer to here, that is the enclosed charge by the surface. And what it means for a charge to be enclosed is that you can't move that charge from inside the, you can't move that charge from inside to outside without passing through the surface, without passing through the Gaussian surface, right? So for Ampere's law, we want something similar. By the way, there's like an accent over the E in Ampere, but I'm going to drop it every time because I anglicize everything. Sorry for anybody who's French. For Ampere's law, we are interested in current enclosed by an Amperian loop. An Amperian loop. So what does that mean for a current to be enclosed by an Amperian loop? So the current is enclosed, just like the charge. The current is enclosed. Oh, and by the way, it has to be like a loop or a line or something. It can't be a surface because this is a loop or a line integral, right? So you have, so whatever imaginary thing you're coming up with has to be one-dimensional, like a line, rather than two-dimensional, like a surface, right? So the current is enclosed if it can't move outside the loop without passing through the loop. So that's the same condition that we had for an enclosed charge. A charge is enclosed if it can't move from inside to outside the surface without passing through the surface. So just as a picture, let's say you have that you have some line of current, some finite line of current, like you just have a piece of wire and you have current running up it, but it's not connected to anything else somehow. Well, if you choose your Amperian loop to be this thing, and remember, this is going to be a choice just like Gauss's law, then you could just take this loop, take this current, and just pop it out, lift it up and take it out. You don't have to cross through the loop at all. So here, this current is, so that's I, this is not enclosed. However, if you have a loop of wire, like a square, with current running through it, I don't know why I'm making these so thick, say that direction, and then you put a loop around it. Let me make it dotted. Now, if you want to get that current outside, there's no way to do it because you'll end up like turning it, and you can't without actually just passing through the loop. So in this case, that current would be enclosed. And by the way, just as a notational or a language definitional thing, sometimes the Amperian loop is sometimes called an Amperian circuit. In the textbook, it's called an Amperian circuit, but I don't like that notation. Loop is sometimes called an Amperian circuit. So there are effectively two ways for a current to not be enclosed by some Amperian circuit or some Amperian loop. The first way is that if the loop has a break in it, so it's not really a true loop, it's not a closed line integral, it just is some line. Like if it was just this, not closed up, then obviously you could remove it out. right? The other way is if the current is on a finite segment and it doesn't form a closed loop. So in this case, the current is a finite segment of wire and it doesn't form a closed loop. So you can just yoink it out and move it outside. Whereas in this case, it does form a closed loop, even though it's still finite. Now, just as an aside, if this chunk of current, if this segment of current was infinitely long, there's no amount that you could lift it up to bring it out. So in that case, the infinitely long current segment would be enclosed. So what we have, now that we've established what it means for current to be enclosed, and we want the equality to be in some sort of current, and it should have this sort of enclosed and not enclosed property that Gauss's law has, we can write down what Ampere's law is. So Ampere's law is the following statement, or it's the following equation. So it's an integral over a loop, a closed loop, of B dot dl. dl, by the way, is the path that goes along the Amperian loop. B is the magnetic field at that point on the path that you're evaluating it. This is equal to, or rather it's proportional to the enclosed current. So we just give the constant of proportionality. It's miraculously equal to mu naught times I enclosed. So this is the enclosed current for that Amperian loop. So this is Ampere's law, the integral form. And just like we found for Gauss's law, there's also a local form that we'll get to later if we get there today, which we'll use more math to get there. Yeah, no, miraculously. I mean, no, this is why that mu naught had a 1/4 pi in the Biot of our law. It's that way then mu naught can play the role of inverse or can play the role of 1/epsilon naught. So there's no extra constants floating around here. So just like for Gauss's law, where we had the integral of E dot dA is equal to Q over epsilon naught for any surface, this is true for any loop. We could have chosen, say, a loop that goes like this, that goes around and then maybe passes in front here and then goes behind there and then goes behind there. We could have chosen any loop and this will still be true. The point is that you have to choose which loop you want to use if you want to use Ampere's law to solve for something useful. So just like you have to choose the appropriate Gaussian surface, you have to choose, yeah, so in this case, you can yoink that out. So the enclosed current is 0, and you could probably imagine why it's 0 because you have current going up and current going down. But it's true for any loop. So you have to choose the appropriate loop to aid your calculational purposes for whatever you're interested in. So let me write down some properties that will be just as a summary of the things that we just talked about. Actually, yeah, this is a useful line to go down. And so a lot of these properties that we're going to write down are very analogous to what we see for Gauss's law, by the way. So an enclosed current, this is just rehashing what we said, means that the current is not able to leave without breaking the surface. Sorry, without breaking the loop. I need to fix that in the lecture notes. Let me just jot that down for myself really quick. Does any closed loop have 0? No, that's the point. Not every closed loop has 0 current enclosed. Some closed loops have non-zero current enclosed, like the one on the right. See, like this green one here, that has non-zero current enclosed because it's enclosing current, right? And you can't yoink that out. Second property, so just like how we had to define what out means for flux when we were talking about Gauss's law, i.e. we had to decide what direction means electric fields go from inside to outside, we need to establish what positive means for this loop. What direction are you going around in the loop that makes it positive? So we define a positive direction of circulation in the loop. Like that's just something that we pick. So for example, in this loop, we might pick that viewed from above, that we might just choose counterclockwise to be the positive direction. And that has consequences on how we calculate, but we need to make a choice. In particular, if the magnetic field has the same orientation, points in the same direction as the positive direction of circulation, then the integral is positive. So to get down to the nitty-gritty, what this amounts to is if you have some Amperian loop, let me draw it in green again. If you have some Amperian loop like this, you have to choose what direction does your vector dl point. And so you might just choose that dl points this way. And so that chooses your positive direction for your positive direction of circulation. And so if the magnetic field, which you take the dot product with dl, if they're in the same direction, then that dot product is positive, and hence the integral will be positive because you'll add up a whole bunch of positive things. That's why there's this notion of the magnetic field pointing in the same direction as the direction of circulation. Likewise, if you choose a direction of circulation that's in the opposite direction of the magnetic field, then you'll get a negative answer. But you'll find that it's not a choice, because if you choose a different direction of circulation, then your definition of positive current changes. And that's exactly what I was going to get to. So there can be both positive and negative currents. Enclosed by a single loop. And the enclosed current, just like for the enclosed charge, but if you have positive and negative charges, the enclosed current is the net current. So you add up the positive current and you subtract off the negative current. Just like in Gauss's law, we're going to use symmetry to solve these types of problems. And again, just like with Gauss's law, the shape, like Gauss's law, holds for any shape, just like it might not be useful, but it still holds. Like the flux through a surface is still governed by Gauss's law, regardless of what the shape of the surface is. The last property for calculational purposes that you'll need to know is that the loop has an out and in directions defined by the right-hand rule. So current that passing through it in the out direction is labeled positive. And current that passes in the in direction is labeled negative accordingly. The way to figure this out from the right-hand rule is you just curl your fingers in the direction of circulation. That we established that you have to just choose. And then the thumb points out. So you choose the direction of circulation, but that affects how you calculate the current. So nothing goes wrong here. If you choose dl to be pointing in the opposite direction of the magnetic field, like let's say you have a wire like this, and say it's some infinite wire, whatever. You have some loop, and let's say you choose it to be that way, right? And let's say the current is going down. So from the right-hand rule, the out direction is up, whereas the current is going down through the loop. So the current would get a negative sign attached to it. The enclosed current is negative. But also, if we were to look at the magnetic field from that chunk of wire, just from what we know, you can stick your thumb in the direction of the current, and that will tell you the direction of the magnetic field. So the magnetic field in this case would actually circulate in the opposite direction. And so you'll get a negative sign from the current and a negative sign from the integral. So those negative signs effectively cancel out. So the point is it's consistent. You just have to account for both effects. You have to account for the effect on the current and the effect on the integral. And you'll find that regardless of which direction you choose to be the positive direction of circulation, you'll still get the same answer, because whatever sign you might have added will be removed. And you'll once you start seeing examples of this and doing practice problems, you'll see what I mean. So let's work through some applications. That's a terrible, terrible handwriting. Right. So there's an example that I linked to in the Young and Friedman textbook. It's the calculation for an infinitely long straight wire carrying current. That's the example that we're about to do. So let's just handle that. Right. So here's the picture. You have an infinitely long straight wire, current, say, running up it. I should put the I on the other side. So let's, before we actually start doing the problem, we have to solve it. So the way that we're going to approach problems like this is we have some wire, and we're going to have to use our brain a little bit to figure out what does the magnetic field look like around this current. In this case, it's a straight wire. And how can we take advantage of that, of the symmetry of the system, to create an imaginary Amperian loop that will let us compute that magnetic field? It's a lot like what we did for the Gauss's law. It's just here, instead of having instead of having electric fields going out from charges, we have magnetic fields that go around currents. So from the symmetry of the system, we can establish the following. We know that if you rotate the entire system, like if you rotate it this way, the system doesn't change, right? It's just an individual wire. It has cylindrical symmetry. So if you rotate it, it shouldn't change. So that means that the magnitude of the magnetic field should be the same at any distance r, at any point a fixed distance r away. So regardless of whether you're over here and that distance is r, or you're over here and that distance is r, this is supposed to be like three-dimensional, the magnitude of the magnetic field that you create should be the same. And that's because there's this cylindrical symmetry problem or property. And it was the same for like a wire, a long line of charge. You have that the electric field is the same at any given fixed distance. What else can we establish? Well, we know, and we've solved this problem before, but we know that the magnetic field circulates around currents. So electric fields come out from charges, magnetic fields circulate around currents. So in this case, the magnetic field circulates around the current in a circular fashion. And it has to be in a circular fashion because there's cylindrical symmetry. Like in principle, you may have thought, oh, well, viewed from above, that maybe it circulates like an oval. But there's cylindrical symmetry, so you should be able to rotate the whole thing without changing it. So it has to be in a circular fashion. And so those two criteria together give us a suggested loop choice. So that the idea that we should choose for a loop is a circle of radius r. So why do we want to choose a circle of radius r? And I'm going to draw this in now. Actually, let me draw it solid so it's a little bit easier to see. And obviously it should be centered on the wire. So why is that the correct choice? And let's give this radius r. Why is that the correct choice? Well, we know that because the r is just some arbitrary fixed radius, because we want to find the magnetic field at some distance. This is exactly what we do for the electric field. We just choose some cylinder of some arbitrary fixed radius, right? And that will let us calculate the electric field at that distance. Right, it's like a variable here. Right, so why do we choose this loop? So we know that the magnetic field, because of the cylindrical symmetry, would be parallel to the line element, whichever line element it is. If it's a line element that points to the left or to the right, it will be parallel to it by symmetry. It might also be anti-parallel, but those have the same notion. The point is the dot product between DL and B is proportional to the magnitudes. It's either equal to the product of the magnitudes or it's equal to the negative product of the magnitudes. And further, we know that the magnitude of B is constant on the loop. So we know that for any place that you evaluate the magnetic field on the loop, the magnitude of the magnetic field is the same. And so we get that same property that we had for Gauss's law, where if the electric field was perpendicular to the surface and it had a constant magnitude on the surface, then you can factor out that electric field and solve for it directly. So that's the same thing that's happening here. So what that implies, or a summary of what I just said, is that the loop integral of B dot dl for this circular loop, well, B dot dl, because B and dl are parallel to each other, this is just equal to an integral of the product of their magnitudes times dl. By the way, we are going to assume that we're picking the direction of the magnetic field of the circulation to be in the same direction as the magnetic field. If we weren't doing that, we would have a minus sign, and we would have to, but we can use the right-hand rule to establish what direction that is. So the direction that we're choosing is the one that corresponds with the magnetic field. And we know what direction that is from the right-hand rule, right? So there's no negative sign built in. That's what I was getting at. And because the magnitude is constant along that loop, we can just pull it out. That should not be a vector symbol. So this is just equal to the magnitude of B times the integral of dl. And the integral of dl, that's just the integral. That'd be like the integral of dx along some line from 0 to x, right? This is just the length. You're just adding up the length along the entire path. So this is the total length of the path. It's the path length of the loop. And we'll just call that L for now. And so what we have is we have that B times L is equal to mu naught times I. Now, again, we have to check here. So we are implying, so we know the magnetic field circulates viewed from above counterclockwise, right? So we're going to choose the positive direction of circulation to be this direction. That is our positive direction. And so we need to double check and make sure that I points in the out direction, right? That I goes out rather than in. And so we use the right-hand rule, curl our hands in the direction of the, I have to use my left hand, curl our hand in the direction of the positive direction of circulation, which is this way. And my thumb points in the out direction. And indeed, the current goes from, the current passes through the loop in the out direction. So the enclosed current is indeed positive I. If we had chosen the opposite direction, the enclosed current would have been negative I. And so the negative sign would have canceled out. Right, and so then all we have to do is figure out what is L. But L is easy, it's just the length of, it's the path length of the loop. It's just 2 pi r. And so what we get is we get that the magnetic field is just mu naught I over 2 pi r. And this is exactly the value that we found last time when we were solving the same problem using the Biot-Savart law. So it's a good check that it works. And indeed, this is a much easier way to compute it, right? You don't have to do any integrals. You just have to you just have to make a good choice, and then it solves itself. Now, there's another example in the Young and Friedman book that's basically the same problem, but instead of just an infinitesimally thin wire with current running through it, it's just some thick wire. So I suggest you take a look at it because that will tell you some more generalized results. It'll be basically the same result when you're outside the wire, but if you're inside the wire, it'll be a little bit different. So another example that we should do is we should verify that Ampere's law holds for a loop of wire. So if you have a loop of wire with current running through it, Ampere's law should still hold for that wire. So let's do another example. This is involving the magnetic field along the axis of a circular loop of current. Right. So we have a circular loop of current going, so here is the back, Here is the front. I always have to do that. So we can't use Ampere's law to solve for the magnetic field along the center line, but we can check Ampere's law with our result, or equivalently check our result with Ampere's law. So whatever loop, so we have to if we want to apply Ampere's law, we have to choose some Amperian loop. So whatever loop choice we choose, it has to enclose the circuit. It has to enclose this current of wire. So like if you imagine just like putting a loop like that, you're not, the current isn't enclosed. You have to have some of the, like you could put a loop like that around the front and back, and that would enclose some. Yes, the Amperian loop can be any shape you want. So we need to find some loop that encloses the current. The trick here is we only know the magnetic field along the center line. So our loop has to be along the center line, right? Has to be something along the center line. I'm going to draw it as a solid line. Has to be along the center line, and that's only because we know what the magnetic field is along the center line. But how do we close this loop? So we don't know the magnetic field anywhere else, right? We don't know that a priori, like we didn't calculate it. So how do we close the loop if we're not allowed to have parts of our loop that like close up? Because if we wanted to use, say, a square like this, we would have to know what the magnetic field is everywhere. We'd have to know what the magnetic field is along this part of the wire, along this part of the loop, along this part of the loop, and so on. So what do? We do something clever. What we do is we say that our Amperian loop extends off towards infinity in both directions. And then once they're infinitely far away, we close it up. We link it up infinitely far away. So our positive direction of our loop goes this way. So the loop choice is a straight wire or a straight line through the center that loops back at infinity. Now, the reason we can do this, so first and foremost, what we can establish is that we know the magnetic field infinitely far away is 0. That has to be true. If it weren't 0, that'd be very confusing. And so what we can do is we can just use larger and larger loops and then take the limit as the size of that loop goes to infinity. And then as we do that, the contribution to the integral from the loop that's infinitely far away will die off because the magnetic field is 0 there. And this, by the way, this is a really common trick that we use in more advanced physics, and it's a trick that's closely related to contour integration. If you know the value of something along an axis, but you don't know the value anywhere else, but you do know that the value decreases with distance, say, from the origin, then you can do a loop integral where your loop occurs infinitely far away from the origin and everywhere. Really neat trick. And so, so now using that loop, we can just plug in and check. We can plug into our Ampere's law and check that it works. So we know that the magnetic field along the center line is mu naught I times r squared, where r is this distance here, over 2 times r squared plus z squared to the 3/2. So here is z equals plus infinity, and here is z equals minus infinity. It's a terrible z. In the k-hat direction, and we know that the magnetic field at infinity, regardless of where you are precisely infinitely far away, we know the magnetic field is 0. Just has to be. So we can do the integral. Let's compute the integral. So the integral of b dot dl for this loop that we've just described would be an integral along the z-axis of b of 0, 0, z dz. So our path length along the z-axis is just dz, has length dz, it points in the k-hat direction. So the dot product will just k-hat dot k-hat, they cancel out, plus an integral at infinity of b dot dl, right? You can break up any loop as just a combination of its segments. And this term is 0 because the magnetic field is 0. And so all we're left with is an integral over the z-axis from -infinity to infinity of dz. I'm going to pull out the constant terms. U naught I r squared over 2. We have r squared plus z squared to the 3/2. And we've done this integral a million times before. So this integral is 1 over r squared, or it's 2 divided by r squared, rather. 2 divided by little r squared. And so what we're left with is we're left with mu naught times I. And then let's just go and double check, make sure that the current indeed does go in the positive direction here. So if we use our right-hand rule, so it's curling from the back to the front. Hold on, let me make sure I get this right. Oh, curling from the back to the front. There we go. Back to the front. That's the direction that we chose to be positive. Sorry, hold on. I'm getting this backwards. Right, so our right-hand rule is for, we apply the right-hand rule for the by the way, the chunk of enclosed current occurs there. So here, this is our enclosed current, because that's the part that's actually passing through the loop. So our loop in green, stick our hand in the positive direction, curl it around in the loop. So the positive direction should be out of the screen. And indeed, at that point, the current is coming out of the screen. And so the current should be positive. So this checks out. We're in the clear. So Ampere's law seems to hold, and it agrees with our result that we derived before, which is excellent. There's another example, which I think you guys should probably take a look at, which is just what is the enclosed current about some arbitrary paths that they give you. This is again in the Young and Friedman textbook. Take a look. It's linked. The last example to do, which unfortunately we're not going to have time to do, but I'll get started on it, is the field inside an infinitely long solenoid. So we want the field anywhere inside an infinitely long solenoid. And I said that the magnetic field is actually, it's nearly uniform. And I told you that I would prove it today. We might not get a chance to prove it, but we'll at least make some progress. And that's just the field anywhere inside the solenoid. So let's do it, and we're going to do it using Ampere's law. So before we can actually calculate what the magnetic field is, we need to establish what the symmetry of the problem is. So for a long solenoid, so we're actually going to have to use Ampere's law twice to establish the symmetry. So the typical picture is you have a bunch of, this is kind of like a sliced view of a solenoid. So you have wires coming in and you have wires coming out on top and on bottom. And so you have like current running like this way. That's the typical sliced view. And so the question is what is the magnetic field? What is the magnetic field doing inside? So we know that along the axis of the solenoid, the magnetic field is constant and it points parallel to the axis. So let me copy that, and I don't know why it took so long to load there. Paste it. So we at least know that along the center line, the magnetic field looks like this. Let me use a different color. Use purple, which is what I've been using. The magnetic field it points in the direction of the axis of rotation, and it points to the right. Now, let me just verify for myself. So we have current coming out. Yeah, so the magnetic field would point to the right here using the right-hand rule, right? So what about off-axis? So we know that the magnetic field shouldn't turn. It certainly shouldn't turn, because if it did, it would make the place where it starts to turn special. And because this is infinitely long, there should be no special place along the length. What there might be is it might be the case that like the magnetic field is stronger near the edges. And so what that would amount to is it would mean that the magnetic field is more densely packed near the edge. That could be a possibility without breaking the symmetry of the problem, right? So we don't currently know how the magnetic field varies with distance to the edge. And that's what we're going to try to first establish. So in order to check this, what we're going to do is we're going to put we're going to use Ampere's law. I don't want that to be green. It will be done in just a minute. I just want to actually, you know what? No, we'll end it there. I'll leave you on a cliffhanger about how we find what the magnetic field is, how it varies inside a solenoid. Let me end recording.